Okay, in this third lesson of mechanics and forces, I want to have a look at trailers and lifts. So last lesson we looked at focusing on trailers. Now I want to look at lifts. Lifts are essentially another version of connected particles, but they're vertical rather than horizontal. So they are the same sort of thinking. Okay, here's my first example I want to look at. So a person of mass 65 kilograms is in a lift of 1,000 kilograms, being lifted by a light cable. They are accelerating upwards at a rate of 2 meters per second squared. And we've got to find the tension in the cable and the reaction force on the person by the floor of the lift. So let's just draw a picture to show you that first of all. So here is my lift. Here is the cable attached to the top of the lift, and it's being pulled upwards. So the tension in the cable is upwards, hoisting it upwards, and it's accelerating at 2 meters per second squared. That's what it said. The other forces we've got involved, there is a person of mass 65 kilograms. So I'm just going to model them as a box. They have got their weight as a force, which is going to be 65 G, or 65 times 9.8 for the force. And we've also got the weight of the lift itself, which is 1,000 kilograms. So that's 1,000 G going downwards. Okay, so that's what our diagram looks like for now. If we resolve the forces then, if we resolve going upwards, we're going to have T minus 65G minus 1000G equals the total mass, which is 1065, times the acceleration upwards, which is 2. If I now go through and solve that equation, 1065 times 2 plus 1000G, so remember that's 1000 times 9.8, plus 65 times G, and that gives me a tension in this cable of 12,567 newtons. Okay. This is a similar method to when we were looking at trailers and we considered the whole system. We've considered both objects together, the lift and the person. To find the reaction force on the person, I'm going to sort of zoom in on just this bit here, the person and the lift. Okay, and I'm going to draw another diagram. So this is the floor of the lift, and this is the person. Okay, so the person's got a mass of 65. Now here, just like we did with the trailer, I'm just going to consider the forces on the person. I'm not worrying about the whole system, I'm just thinking about the forces on the person. So the person has got their weight of 65G, and they've also got a reaction force upwards, which I'm just going to call R. Okay, let's make that a bit clearer. R. Think about when you just stand on the floor. Forget about it being a lift. Normally when you stand on the floor, your weight acts downwards, and then there is an equal and opposite force upwards on you, which is the reaction force. And that force needs to be there because otherwise you would sink through the floor. There needs to be an equal and opposite force to keep you steady. Now in the case of a lift, that force R is still there. The person is not falling through the floor of the lift, so there must still be an R there. But we've also got the context that they are moving upwards and accelerating upwards at 2 meters per second squared. So we can still do the same thing. We can resolve our forces upwards. So the upwards force on the person is force R, the reaction force from the floor, minus 65G equals their mass, which is 65 times A. So if they were stationary, just stood on the floor, and they weren't accelerating, that would be 65 times 0, and then you could see that R would then be 65G, the same as their weight. It would be equal and opposite. But because we're accelerating upwards, this is 65 times 2. And I can then resolve this to find R. 65 times 2 plus 65 times 9.8, which is 767 newtons. And that's the reaction force from the floor of the lift on the person's feet, pushing them upwards. In this second example, this is basically exactly the same as the one we've just done. So a person is 65, the lift weighs 1,000. But this time it's moving upwards but decelerating at 2 meters per second squared. So we're still actually moving upwards, but it's just slowing down. Perhaps it's reaching the floor where they want to get off, so they have to slow down, but they're still moving up. So I'm going to draw the diagram again. Here's the lift. Here's the person, cable with tension T, put their weights on. And then for the acceleration, I'm still going to label it like that because they're still moving up. But then I'm going to write the acceleration as minus 2 meters per second squared because they're decelerating. And we're going to work out the tension again, and we're going to work out the reaction on the person's feet as well. So if we consider the whole system going upwards, T minus 65G minus 1000G, because the total mass, which is 1065, times the acceleration upwards, which is minus 2. Okay, so let's work out what answer we get. So I get 8,307 newtons. Okay, now the answer before that we had previously, when it was accelerating upwards, was 12,567 newtons. So you can see that this is a lot lower value because it's not having to not only lift it and accelerate it, which takes lots of force. It's just got to basically lift it upwards, but it doesn't have to do any extra effort in actually making it accelerate upwards. Okay, so we require a lot less force upwards. If we now think about the force on the person inside this lift, so again I'm going to sort of zoom in on the person inside the lift. So they've got a force downwards with their weight, 65G, and there's a force upwards from the floor, which we're just going to label R. They're accelerating upwards. Well, sorry, they're moving upwards, but acceleration is down because it's decelerating, so it's minus 2. And now we're going to do the same thing, but just considering the forces on the person. So I've got R minus 65G equals 65 times minus 2. So now if I solve that to find R, I get 507 newtons. Okay. Now compared to before, when they were accelerating upwards, we found the reaction force was 767. So the force on the person is also reduced. And this is why you might have experienced this yourself. When you're going in a lift, you can feel heavier or you can feel lighter depending on what the motion of the lift is like. So when the lift is accelerating upwards, so perhaps when it first sets off, you feel heavy. You can feel the weight of the lift pushing on you. When you get to your floor, you sort of feel a little bit, not weightless, not like you're in space, but you definitely feel a little bit lighter as the lift is slowing down. And that's the reason why the reaction force on you is actually less. Now we can demonstrate this if you actually go in a lift and if you take a pair of scales with you, which sounds a bit mad, but that's what I did. So here's a video of me. This is in the lift at college. And I took a pair of scales in with me to show what my weight appears to do when I'm in the lift. The reason why this happens is because what a set of scales basically does is it measures the reaction force. Okay, so you can think of a pair of scales as showing you the reaction force. Now normally if you're just on stable ground, the reaction force is the same as your weight. But if you are accelerating upwards or downwards, the reaction force changes. So we can watch this video and see what happens.
Right, going up. Now we're at the top, so it's slowing down. Now we're at the top. Right, back down. Ooh, another one. And slowing down.
Okay, so hopefully in there you saw my weight is sort of shifted by about plus or minus 5 kilograms, about that much, which is quite significant. So that's to do with when I was accelerating upwards, it made me appear heavier, and then when it was decelerating or accelerating downwards, they're both the same thing, it made me feel a lot lighter. Okay. Okay, so based on this concept of changing your apparent weight when you're in a lift, here's a question. So Jamie is attending a local weight class club, and it's on the 5th floor of the leisure centre. And I've got to report my weight each week, but I'm running a bit late, and so I brought my bathroom scales with me, and I was just going to weigh myself in the lift on the way up. So assuming that my actual mass is 70 kilograms, and that the maximum acceleration or deceleration the lift can get to is 2 meters per second squared, what is the lowest reading of my mass that I can get from my scales? So let's draw a picture. I'm just going to focus on the lift and me. So I'm just going to I'm not worried about like the tension in the cable or anything like that. So I've got the actual weight downwards, which is 70g. I've got the reaction force upwards, which is what the scales basically measures. So it can either be A equals 2 upwards, or it could be as low as minus 2. Okay, maybe we'll consider both. Okay, so if we do it when A is 2, so when the lift is accelerating upwards at its maximum acceleration that it can reach, we would have R minus 70g equals 70 times 2. When A is minus 2, so when the lift is slowing down, or it could be when it's accelerating downwards as well, we can have R minus 70g equals 70 times minus 2. Now hopefully out of those two you can predict which one is going to have the higher or lower R, but we will work out both anyway. So if A is 2, then R would come out as 826 newtons. And when A is minus 2, R comes out as 546 newtons. Okay. So obviously when the lift is slowing down would be the time for me to take my measurement. We need to convert this into a mass though. These are just forces. I doubt my weightless club would be very impressed if I turned up and said my weight this week was 546 newtons, even though I'd be technically correct. We need to turn this into a mass. So remember, normally the mg gives you your weight. So to go backwards, I need to just divide by g. So 826 divided by 9.8. And that gives me 84.3 kilograms. So that would be my maximum weight that I could measure. Over here, 546 divided by 9.8. It's going to give me 55.7 kilos. Okay, so that's quite a big difference. It wasn't quite as big as that when I did it in the lift in that video, was it? But I guess it depends on how strong your lift is, how fast can it accelerate up or downwards. Okay, in this next problem, it's got a slightly different context. So still some objects in a lift. It's described as a light scale pan. A scale pan is just like a dish that you would lift objects up in. It's attached to a vertical, light, inextensible string. The scale pan carries two masses A and B. You can see them in the diagram there. The mass of A is 400 grams. That G there is for grams. So I'm actually going to relabel this, I think. Rather than 400 grams, I'm going to write it as 0.4 kilograms. Okay, then this other one is going to be 0.6 kilograms. Just so we don't get confused with our G's and grams. Okay. A rests on top of B, as shown in the diagram. The scale pan is raised vertically using the string with an acceleration 0.5 meters per second squared. Okay, so we've also got a tension in the string here, just like I did for my other lift questions, because it's being lifted upwards. I'm going to draw on the weights as well. So I've got 0.4 g, 0.6 g, so that's its mass in kilograms times acceleration due to gravity. It says that it's a light scale pan, so I don't need to worry about the mass of the actual lift here. So part A, find the tension in the string. We're going to do what we did before. We're going to consider basically the whole system, and we're going to resolve upwards. So I've got T minus 0.4 g minus 0.6 g equals the total mass, which is 1 kilogram, times the acceleration upwards, which is 0.5. Okay, and if I solve that, then I will get 10.3 newtons. Okay, so there's my answer for the tension. Part B, find the force exerted on mass B by mass A. So the force on the bottom box by the top box A. Okay. Now, if it wasn't accelerating upwards, so if these were just objects on the ground, the force exerted on the bottom box by the top one, well, that would just be the weight of the top box. That seems straightforward. But because we're accelerating, that makes things a bit more confusing. So what I'm going to do is I'm just going to draw a diagram showing these two boxes, and we're just thinking about the forces on the boxes. Okay. So this one's 0.4, this one's 0.6, and we know the whole thing, so both boxes stacked on top of each other, are accelerating upwards at 0.5 meters per second squared. And then we've also got the floor of the lift here as well. Now, an important thing to understand here is there is a reaction force between the two boxes. Okay, we've got the weight of box A pressing down on box B, but there's also going to be a reaction force upwards. Okay, because if there wasn't, then box A would basically fall through box B. It would sort of squash through it. So there must be a reaction force upwards. So we've got a force here and a force here, and they must actually be the same. Because if they weren't, then the boxes would either be separating or they would be running into each other, but they're not. They're just moving together at the same rate, like they're stuck together at this point. So these two forces here, at the interface between A and B, are exactly the same. Because if they weren't, they'd either be pulling apart or they'd be crushing into each other. So that's an important thing to understand. So the force on B by A, which is this downwards R, is actually exactly the same as the force on A by B, which is the upwards R that I've put on here. Because if they weren't, then they'd be crushing each other or they'd be coming apart. So now what I'm going to do is I'm just going to look at the forces on box A. And again, this is a bit like when we did the trailer questions. We just looked at the forces on the caravan or just the forces on the car. So I'm just looking at the forces on A. If I resolve upwards, then I'm going to have R minus its weight, so 0.4 g, and that equals ma, so that's 0.4 times 0.5. And then I can solve this to find r, which is 4.12 newtons. And this upwards r is exactly the same as this downwards r here. So that would be the same as the force on mass B by mass A, so 4.12. Okay. Part C, the force exerted on mass B by the scale pan. I'm going to do a similar sort of thing here, but I'm interested in the forces between B and the floor of the lift. So what I'm going to do is I'm going to just treat this as one big box like that with mass 1 kilogram. Okay, still accelerating upwards at 0.5. Now the forces here is the weight downwards of both the boxes, because the weight of both the boxes is going to act on the floor of the lift. So this is 1g, and then we've got a reaction force from the floor of the lift on box B, which is at the bottom, which I'm just going to call R. Okay, and that's what we're interested in, is find the force on mass B by the scale pan. So we're trying to find out this force R. So now we'll resolve. And again, we're considering the forces on box B. So upwards, we've got force R minus 1g equals the mass, which is 1, times the acceleration upwards, which is 0.5. So R would be 10.3 newtons. Okay. So there's a few different strategies and a few different ways you can consider the different forces. But hopefully you can spot that it is a similar type of analysis to that we did for trailers, where you consider either the objects together or you consider the objects one by one and just the forces on that one object. It can be conceptually difficult with lifts sometimes, especially things like in part B. Okay. But once you've done a few practice questions, you'll get the hang of it. You might also notice in this question, the reaction force on the bottom of the objects from a scale pan was the same as the tension. Well, perhaps you can imagine this diagram like this. If this force here is T, and you've got your boxes here, that force T is also being applied here, which is, to some people that seems obvious, to some people that doesn't seem so obvious, but I've had students in the past that could see that sort of straight away. Well, if this T is 10.3, then the force on the bottom of the scale pan upwards must also be 10.3. So you might have spotted that. Okay. Here's a similar question for you to do. I've put the answers at the top as well, but I will go through it in a minute. Have a go at this one on your own and make sure you can get to those solutions there, and I'll go through it in a second. Okay, so in this question, I'm just going to draw myself a diagram out. There's a few things that are different in this question compared to the last one, but the method is the same. Okay, so here's my lift. I've got the cable up here. I've got my two boxes. Box A, box B. So A was 110 and B was 190. Now, if we label the forces on here, we've got the weight of box A, which is 110g, the weight of box B, which is 190g, and the weight of the lift as well this time, which is 1700g. Okay. It also told me it was descending, so it's moving down this way with a constant acceleration of 1.8. So it's moving downwards and it's accelerating downwards at 1.8 meters per second squared. The tension in the string still goes up though. The reason for that is the cable is there to stop it just falling down to the ground at 9.8 meters per second squared, which would not be good. So the force in the cable is still upwards. It's trying to slow this object down. So if we consider the whole system, and I'm going to resolve downwards this time just because that's the way it's moving. So I would have 110g plus 190g plus 1700g minus the tension in the cable equals the total mass, which is 2000, times 1.8. Okay, and it's positive 1.8 because I'm resolving downwards and the acceleration is downwards. So if I solve this to find t, I'll get 16,000 newtons. Okay, so that's the tension in the cable. For part B, we've got to find the force exerted by box B, so by the bottom box, on box A is the first bit. So let's zoom in on these boxes here, because what I'm interested in this question is what's going on here, the forces between A and B. So I'm looking at this interface here. So let's just draw that out. So the whole thing's going, well, accelerating downwards at 1.8 meters per second squared. The bottom box is 190, the top box is 110. Now remember in the last question, we talked about when we're thinking about just the forces here, at this interface between A and B, they are balanced. Even though it's accelerating up and down, the two boxes are moving at the same rate as each other. They're not crushing one another and they're not going through one another or floating off, one flying away from the other. So there's a force here and a force here, which must both be the same. Now I'm going to just consider the forces that act on box A. And I'm going to consider the forces that act on box A downwards. So I've got its weight, which is 110 G. Then I've got this force R upwards, which is the reaction force coming from box B. You could maybe think of box B as being like the floor for box A. So minus R equals 110 times 1.8. Okay, and if I solve that to find R, then I get 880 newtons. Okay, and the R upwards would be the same as the R downwards, like we discussed, because they're not going through each other and one's not floating away from the other. So that's the answer there. It asks for the force from box B on box A. So I suppose that's technically there's upwards force here, so you could say 880 newtons upwards. For the second part, the force by box B on the floor of the lift. So now I'm just thinking about the forces between the floor of the lift and the box itself. So I'm just going to draw a diagram for that. I'm going to treat both these boxes together because the weight of both the boxes acts on the floor. So when I consider both of them together like this, I can just consider them as having a mass of 190 plus 110, which is 300. Okay, and there's a weight going downwards of obviously 300 G, and then there's a reaction force from the bottom of the lift on these objects of R, and that's basically what I'm trying to find, is force R. So if I resolve, I'm going to go downwards, so that'd be 300 G minus R equals the mass times the acceleration downwards, I forgot to put that on there, of 1.8. So then R is 2,400. Okay. So this force here, the reaction force between B and the floor of the lift, is 2,400 newtons. Okay. I'm going to set you some questions which aren't in our normal textbook. They're from actually a different textbook, but I will upload a PDF of those questions for you to have a go at. And I've also got some work solutions as well, which I'll link next to the video.